In this lecture segment, we'll continue the walkthrough of Mastermind's target function. And we're going to look at various concepts. We'll look a little bit more closely at the number type. We'll also look at the whole idea of elemental types, like number and string versus objects. And then we'll look at something called method cascading. So, starting with the number, continuing our Mind.js walkthrough, let's look at a bit of the JS math on lines 14 through 16 here. These compute and report the running average based on total tries, which we initialized up here, and numGames. Total tries is the number of guesses made across all the games thus far, and numGames is the number of games played so far. And these variables are numbers, of course, as we mentioned earlier, and the division here on line 14 thus does the obvious thing to compute an average. But it is worth noting that Java has no integer type. Number values are all effectively like C or Java doubles. If you want an integer value, you store it as a double with a 0.000 fraction. So there's no question of integer division. JS division never truncates the fractional part. And JS is not designed, by the way, for intense mathematical computation. The big advantage of an int type versus a double in other languages is that ints are much faster. And JS doesn't care enough to include an int type for speed. It would rather you have the convenience and the simplicity of a single number type, even if that limits your choices for speed or for memory size. Now the line 15 through 16 print is a little different from earlier prints. In particular, if you parse the line carefully, you can see that there are three parameters. There's the first one, and there's the second long one, and of course play a game is the third one there. The first and third are clearly strings, and the second is also, as we'll see. Print takes as many string parameters as you like and automatically concatenates them into a single long output string. You can concatenate your strings with plus, or you can concatenate them by passing them as separate parameters, or you can do a little of each, as I do, for instance, on the line 29 print down here, just to kind of make the point. So this second parameter does need a bit more discussion. It's a conditional expression, and that, as you know from other languages, is a test followed by a question mark, and then two choices, NA in our case, or this average thing we'll talk about more closely, separated by a colon. It's a sort of if statement in an expression, like its cousins in Java or C. If the test is true, you get the first alternative before the colon. If the test is false, the second after the colon. This particular one chooses NA if the average is a nan. And then a quick reality check in lecture question. How and when will that NA be chosen in the actual run of Mastermind? Coming back from a pause there, should be fairly obvious based on our earlier NaN discussions. The first time around, we'll have 0 for both operands of the division. They're initialized that way. So we'll always get a NaN at the first loop iteration before we play the first game, and thus always show NA for that. So let's look more closely here now at the average.toPrecision call. What's that about? Now, if average were an object reference, like params, for instance, and its target object had a toPrecision method, well, then this expression would make perfect sense. But I said earlier that numbers, like average, are elementals, not objects. So do elemental values have methods then? No, they don't. And here you'll find this lecture differing with some other JS presentations that kind of gloss this issue over, and they'll just tell you, oh, elementals are also objects and they have methods. The truth is importantly different from that gloss over, and the difference is critical to understanding some odd behavior that surrounds JS elemental data. We'll go over it lightly here and more intently in a later lecture. Here's the deal. When you use an elemental as though it were an object, like here, JS spontaneously creates an object for you. This object has a property holding the original elemental, like our average value in this case, and it has several dozen utility methods, or maybe a dozen or so, for use with that elemental property. Let's call this a wrapper object. Each elemental type, number, string, Boolean, has its own wrapper object type with appropriate methods for that elemental type. Now, wrapper object is the standard JS term for this concept, but the notion of enclosing an elemental value in a more powerful object appears in many other languages, and it's usually called boxing. In Java, for instance, boxing is done via the wrapper class's integer float double with capital letters at the beginning. Recent Java versions will even create the wrapper objects automatically and transparently when needed, just like JavaScript does. I've added a diagram of the wrapper object here, assuming we executed average.toPrecision of 2 with average holding the value 3.14. The wrapper has a property I'll call value, and that holds the actual numerical value, and another for the toPrecision method, which points to a function object. Now, in practice, there would be a lot more such function properties. This wrapper object is what the toPrecision call is made on. The toPrecision method returns a string, not a number, representing in text form the number in question, written to 2 decimal digits of accuracy. So in the final estimation, the 2 alternatives for our conditional are both strings. Now, once the method call returns, very importantly, the wrapper object is destroyed. So it's a very ephemeral object indeed. Goodbye. You wouldn't even know it existed. And you could get by with the gloss over elements or objects of a sort that I kind of sneered at earlier, were it not for the fact that you can create wrapper objects of your own that are more permanent. So unless you're really clear on the difference between an elemental value and a containing wrapper object that you created, you'll smush them together in your mind and your visualizations, and you'll get very confused in certain more advanced situations. For instance, let's try question 2 here, the following in a JS shell. Experimenting around a little here. Let's create a variable, x, and then let's do x bracket new property. Remember from our discussion that that may add a brand new property if there isn't one already to it. 42. All right. And we get a little 42. And now we're going to print x bracket new property. Thus, undefined. Now, explain that as a in-lecture question. The third line prints undefined. What happened? Did the property assignment fail somehow? And just a hint, you can't apply brackets to elemental data. You can only apply it to objects. This is an important in-lecture question, so think carefully until you're confident you have an answer, if possible. The answer is, on the second line here, the JavaScript created a new wrapper object to contain the x, and then applied the brackets to it and added a new property successfully. But then it blew the wrapper object away at the end of that line. And on the third line, it did the same thing again. It created a new wrapper object. This new one doesn't have a new property entry, of course, or new property, and it came up with undefined for that property. It works the same, by the way, with dot notation. I just used the bracket notation because I thought it would be a little more obvious that a wrapper object would be needed. Now, perhaps this exercise makes it clear why you need to understand wrapper objects to understand what JavaScript is up to in these cases. Now, line 17, let's kind of move on here, reads and parses the reply to the play a game prompt. It's a pretty elaborate line for the simple task of checking for a lower or uppercase y, but JavaScript text input is remarkably weak since text I/O is not JavaScript's real purpose in life. So we end up compensating for that, and along the way we get a tour of some string methods. First, the only way to read input is line by line via the built-in global function readLine, which returns the next line of input. Now, this string might start with some white space before a useful letter, so we call trim on it. Trim on the result of readLine. This returns a string with all leading and trailing white space removed. Now, the trimmed string might have upper or lowercase letters in it, and to simplify checking, I want to convert it to uppercase only, which we do by calling toUpperCase in turn on that, which returns a third string value with only uppercase letters. We want to know that this one starts with a Y. We want to check the first letter of it. We'll ignore any trailing letters in the response. So we call char@ with a 0 to get its first character. They're numbered from 0, just like an array. All four of these methods return an elemental string, which means the return of each can be used as the basis for the next call. And suites of methods are sometimes designed like this, so that each returns data that can be the starting point of the next method call. And you get a kind of pattern with this dot that, progressively changing the data. This is termed method cascading, and it's quite popular in JavaScript. You'll see a lot of it. Now, here's question 3 for you. I've described this method cascade as though each elemental string in the sequence had methods. But we know that's not exactly true. How many distinct objects, not just elemental strings, are created and destroyed by the method cascade that we just looked at? Coming back from a pause, a total of 3 wrapper objects are created and then destroyed, one each for the calls of trim, toUpperCase, and char@. Okay, the final result of this cascade is the first non-blank character of the line in uppercase form. Now, in many languages, including Java and C, there is a special type for character, but JavaScript has none. A single character is just represented by a one-character string. So we're comparing the cascade result against the string single y, and if it differs, we break from the loop to end the program. Otherwise, we continue on to play a game. An equality comparison in JavaScript is done with the rather odd-looking operators triple equal sign for equality and bang double equal sign for inequality. There are also operators double equal and not equal, which I've used up to this point to avoid confusion, because they look more like equality comparisons in traditional languages. But in fact, those are poorly designed, and you should not use them. From now on, we'll use the triple equal and bang double equal operators. Now, when comparing elementals, you get a deep comparison of the actual values, which is what you'd expect. But when comparing references to objects, you get a shallow comparison. The two variables are equal only if they refer to exactly the same object, not to two different objects with identical content. There is no standard way to do deep object comparisons in JS. There's nothing analogous to Java's .equals method, for instance. You have to handcraft your own. This is probably another JavaScript design mistake. So finally then, a bit of external research. Look up the wrapper classes for strings and numbers, the wrapper objects I should have said. They're called capital string and capital number. Those are actually the name of their constructors, which we'll get to later. Find out what other methods they have, and answer these 2 in-lecture questions based on your research. Question 4. What if I want to drop trailing space, but not leading space, from a string, say we'll call it text? How do I do this? Going back from a pause, that would be test.trimRight. And then question 5. The toPrecision method doesn't really do what I want. I put it in there kind of as a ringer so I could ask a question a little later here. It actually rounds to 2 places of accuracy, not to 2 decimal digits after the decimal point. For instance, if I take 12.45 and do a .toPrecision 2 call on it, and by the way, you can call toPrecision on direct constants. Again, it'll just box the constant to do that. So if I call this, kind of putting it in the slide here briefly, thus, it results in 12, not 12.45, 2 digits of accuracy. So find the right method, please, to ensure exactly 2 decimal digits after the decimal point. And coming back from a pause, and that would be 2 fixed of 2, or passing 2 instead of 2 precision of 2.